On the 7th of January 2026, a research team published a result that made astronomers pause. A galaxy cluster called SPT 234956, existing when the universe was only about 1.4 billion years old, yet already surrounded by an atmosphere of gas heated to at least 5 times hotter than what current models predict for such a young cluster. This wasn't a stray star, not an odd galaxy, but an entire city of galaxies, radiating heat as if the universe had turned on the furnace far too early. Scientists detected this hot gas through the subtle shadow it casts against the leftover radiation from the Big Bang. A delicate, dark imprint, but one strong enough to suggest that an enormous energy source is pumping heat into the cluster's environment, possibly powered by violently active supermassive black holes. And this is where James Webb enters the story like a new kind of lighthouse. Not to repeat what we already believed, but to shine directly into the earliest stages of cosmic history, where the universe should not yet have had time to mature. If a galaxy cluster can already be too hot, too early, then the other impossible things Webb keeps uncovering galaxies that are too bright, too large, too evolved. Black holes that are too massive may not be exceptions at all. They may be signs that we are living through a rare moment, when new data is beginning to force the entire old story of the universe to justify itself. The universe did not begin by confusing us. It began by letting us believe, for a while, that it could be arranged neatly on a whiteboard. For a few decades before Webb opened its golden eye, astronomers lived in something rare in science: a period of quiet confidence. The outlines of the cosmic story felt settled. There was a beginning. There was an expansion. There was a timeline that stretched from an almost unimaginable hot fog to the calm spiral of a galaxy like our own. The numbers behind that story were precise enough to print in textbooks, to teach to children, to fold into planetarium shows and documentaries. The universe, according to that map, was about 13.8 billion years old. Not eternal, not arbitrarily old in a very specific way. The Big Bang picture, once controversial, had matured into something more like infrastructure. You could doubt the details. You did not doubt that the universe began in a dense, hot state and has been expanding and cooling ever since. On one April day in 1990, a telescope rose above the atmosphere and gave that confidence a lens. The Hubble Space Telescope left Earth on a space shuttle, was released into low orbit, and began a new phase of astronomy. One where the air no longer blurred the view. For the public, Hubble quickly became a symbol, not just of science, but of a certain kind of optimism. A metal cylinder circling the planet, sending down sharp images of nebulas and galaxies that looked almost staged. Those pictures hid something important behind their beauty. They were not only posters, they were measurements. Hubble's sharpness allowed astronomers to estimate distances more reliably, to track the brightening and dimming of special kinds of stars, and to refine the rate at which the universe expands. All of that fed back into the idea that we lived in a cosmos that could be understood in equations and plots. A few years after launch, Hubble was pointed at almost nothing. In late 1995, astronomers chose a patch of sky near the handle of the Big Dipper, a region that looked empty even to large ground telescopes. And they did something that, at the time, felt slightly reckless. They told Hubble to stare. For about 10 days of combined exposure time, the telescope collected light from that apparently blank area. To anyone outside the field, it sounded like a gamble. Why waste precious observing time on nothing? When the data were combined into a single image, the gamble evaporated. That empty patch resolved into thousands of galaxies. Some were smooth and featureless, others were warped, clumpy, irregular. Many were so faint that only a telescope above the atmosphere could see them at all. The Hubble Deep Field, released in 1996, did something that equations alone had not done. It turned the early universe into a photograph. You could look at that image and feel an almost physical shock. This is what the sky looks like if you peel away the nearby stars. Every point, a collection of billions of suns. Some of the light had been traveling for billions of years. What looked like a sprinkling of grains was, in fact, a census of cosmic history. The deep field became a template. Point, stare, stack, and count. Each deep pointing of Hubble added to a statistical picture of how many galaxies exist at different distances, how bright they are, how they change with cosmic time. It was the observational backbone behind a simple narrative. Small structures form first, then merge. Over billions of years, galaxies collide, feed, settle, and grow into the rich zoo we see today. Around the same time, another piece of the puzzle fell into place. In the late 1990s, two teams of astronomers used distant exploding stars, type Ia supernovae, as standard candles to measure cosmic expansion. They expected the expansion to be slowing down, pulled back by the gravity of all the matter in the universe. Instead, in 1998, their data told a stranger story. The expansion is speeding up. You can imagine the mood in those meeting rooms. Plots that refuse to lie flat. Data points drifting away from the lines everyone had drawn. For a while, the result was treated with caution. It could have been a systematic error, something mundane in the way the supernovae were selected or calibrated. But as more observations came in, the pattern held. The universe is not just expanding, it is accelerating. To account for that, cosmologists reached back to a term that Einstein had once introduced and then set aside: the cosmological constant. Reinterpreted, it became a way to describe a uniform energy that fills space itself. Dark energy, not in the sense of something sinister, dark only because it does not shine, does not clump, does not behave like normal matter. In the standard model that rose from these results, often called lambda cold dark matter, dark energy dominates the energy budget of the cosmos. Most of the universe, by content, is something we cannot touch or see directly. In 2011, the Nobel Prize in Physics went to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of the accelerating universe. For many physicists and astronomers, that award felt like a kind of seal. Not that everything was solved, but that the broad strokes were now official. Big Bang, expansion, a universe governed by general relativity, dark matter sculpting the large-scale structure, dark energy steering the overall fate. By then, another background had been mapped in exquisite detail. The cosmic microwave background, the afterglow of the hot early universe. Satellites like COBE, WMAP, and later Planck turned the sky into a baby picture of the cosmos. Tiny temperature variations across that ancient light showed how matter was distributed when the universe was only a few 100,000 years old. Those maps, combined with theory, let cosmologists run the clock forward in computers. They built simulations, first with only dark matter, letting particles of invisible mass attract and form a skeleton of clumps and filaments. Then with gas and stars and feedback, making the simulations more realistic. These N-body and hydrodynamic runs painted a consistent story. Small dark matter halos form first. They merge. Over time, larger halos appear. Galaxies grow inside those halos over billions of years, forming stars, building disks, generating spiral arms and central bulges. Extremely massive galaxies in the very early universe did appear in the simulations. But they were rare creatures, sitting at the long tail of probability. In this framework, you could make charts. You could predict how many galaxies of a given mass should exist at a given epoch. You could predict how quickly stars should form on average, how metals should build up as generations of stars live and die. The match between those simulations and the observed universe, especially at modest distances, was good enough to be comforting. The cosmic story looked like a clean storyboard pinned on a wall. On the left, the smooth fire of the early universe, nearly uniform. Then, slight ripples growing into a cosmic web. Then, knots where galaxies form, gradually becoming more complex, more structured. Somewhere along the way, stars gather heavy elements in their cores. Later, planets assemble from disks of dust and gas. Later still, life may appear. The order could be debated in detail, But the sequence had a tidy logic. Outside the equations, culture carried a similar feeling. In 1968, long before Hubble, a film reached theaters that captured a particular way of seeing the universe. 2001. A Space Odyssey showed space as vast and indifferent, but not chaotic. The monoliths in that story arrive at specific milestones: human evolution, orbital flight, a journey beyond Jupiter. The universe is not simple, but it is orderly. It progresses. By the time Webb was being prepared, that cinematic sense of an orderly cosmos had merged with the scientific one. We had an origin, a timeline, a set of parameters that seemed to lock together. People grew up with posters of Hubble's images on their walls, with documentaries that explained dark matter and dark energy in polished graphics. The universe, while mysterious, behaved in ways that made sense on a plot or a slide. When you live inside a story like that for long enough, something quiet happens. Anomalies start to feel like noise. A strange galaxy here, an odd cluster there. You assume they will be folded into the main arc eventually, or explained by some overlooked detail in the data. The human brain is good at smoothing rough edges when the big picture feels secure. Simulations reinforce that feeling. When a model reproduces not only the overall distribution of galaxies, but also their clustering, their approximate sizes, their rotation speeds, it is tempting to lean back and say, this is close enough. The universe might be more complicated in the margins, but the scaffolding is sound. In that mood, Webb was not born into a blank space. It emerged into a room where the furniture was already arranged. Cosmologists had a concordance model. Observers had deep fields and distance ladders and calibrated supernovae. Instrument builders had decades of experience turning photons into data. The story on the wall was not perfect, but it was coherent. And then we built a telescope that could see further into time, deeper into dust, more sharply into the infrared than anything before it. A machine that was never going to be satisfied with the tidy storyboard. It did not arrive to decorate the existing picture. It arrived to test how much strain that picture could bear before it began to tremble. The picture on the wall was steady. So when engineers and scientists decided to build a new eye for the sky, they were not only adding another frame, they were quietly preparing a tool that might press a thumb against that picture and feel for cracks beneath the paint. In the mid-1990s, while Hubble was still young and the first deep fields were being assembled, a phrase began to circulate in conference halls and planning documents. The Next Generation Space Telescope. It sounded vague on purpose, a promise more than a blueprint. The basic idea was simple and ambitious at the same time. Build a telescope that could see further into the infrared than Hubble, with a mirror large enough to collect the faintest possible light from the first galaxies. The early studies did not yet have a name like James Webb attached. They had sketches, concepts, mirror sizes drawn on napkins and whiteboards, ideas about sunshields and deployable structures that, at the time, felt closer to science fiction than hardware. Space agencies, especially NASA, began to test the boundaries of what was mechanically possible. Could you fold a mirror large enough to transform our view of the universe, cram it inside a rocket, and then unfold it flawlessly in space? In 2002, the project was renamed the James Webb Space Telescope after a former NASA administrator who had helped steer the agency through the early years of human spaceflight. Giving it a personal name made the project feel more real and also more exposed. From then on, it was no longer a sketch. It was a promise. This is the telescope that will see the first galaxies. The road between that renaming and the actual launch was long and rough. Budgets swelled. Technical challenges multiplied. At various points, the project came close to being cancelled. In meetings far from the stars themselves, people argued over cost, over risk, over the wisdom of investing so much in a single machine. Newspapers and magazines wrote about delays. Some framed Webb as a troubled symbol of overreach. Others as a test of how much patience science deserves. Inside the teams building it, the mood was more intimate and more anxious. Engineers had to design mirror segments that could change shape by tiny amounts at cryogenic temperatures. Instrument teams had to build detectors that could feel whispers of infrared light without being drowned by their own warmth. Every extra complication was a new way for the mission to fail, but every simplification threatened to weaken what the telescope could do. Eventually, the pieces began to come together. A hexagon of hexagons. 18 gold-coated mirror segments. Each one polished with a precision hard to imagine. Each one mounted on motors and actuators that could adjust its shape and tilt by amounts measured in nanometers. Behind them, the instruments, cameras and spectrographs designed to work in wavelengths, from the reddish edge of visible light out to the mid-infrared. Around them, a 5-layer sunshield the size of a tennis court, shaped like a kite, designed to keep the telescope so cold that its own glow would not drown out the faint light it wanted to capture. On December 25th, 2021, an Ariane 5 rocket rose from French Guiana with a folded telescope in its nose. The timing, so close to the end of the year, gave the launch a strange double feeling. It was both a technical event and a kind of ritual. People watched from living rooms and control rooms as the rocket climbed, separated, and released the observatory into space. Hubble had once been launched into a low orbit where astronauts could reach it with a shuttle and fix what went wrong. Webb was different. Its destination was far beyond the reach of any crude repair mission. The second Sun-Earth Lagrange point, often shortened to L2, about 1.5 million kilometers away from Earth, in the direction opposite the Sunday. At that location, the observatory could orbit in a delicate balance, with the Sun, Earth, and Moon all on the same side of its sunshield. Light and heat on one side, deep cold on the other. The choice of Lagrange point L2 was not mainly about distance as a dramatic number. It was about stability and temperature. To see very faint infrared light, the telescope had to be cold, colder than ice, colder than many regions of open space. The giant sunshield, once deployed, would block direct sunlight and reflected light from Earth and the Moon, letting the telescope radiate its own heat away. In that permanent artificial night, the mirrors and instruments could cool to the point where their thermal noise became small enough to tolerate. Getting there was the easy part. The hard part came after the rocket did its job. For days after launch, Webb was a sequence of unfolding actions. First, solar panels and communications antennae. Then the careful release and tensioning of the sunshield layers, one after another, like opening a very fragile umbrella in slow motion. Then the deployment of the secondary mirror on its long spider-like support. Then, gradually, the release and fine positioning of each primary mirror segment. None of this could be practiced in full in space beforehand. There were tests on the ground, of course. Simulations, thermal vacuum chambers. But the exact choreography of a multi-week deployment had to work the first time. If a hinge jammed or a cable snagged, there would be no astronauts to go up and nudge it. The phrase "too big to fail" circulated in media coverage, and in a way, it was backwards. The mission was too ambitious not to risk failure. The only way to do what it promised was to trust that every bolt, motor, and sensor had been built and tested well enough. As each stage completed, relief spread through the teams watching. Yet, with relief came a new kind of pressure. A successfully deployed telescope was not the end of risk. It was the beginning of accountability. Once the mirror segments were in place, the long process of aligning them began. Using bright stars as guides, engineers adjusted each segment until they acted as a single mirror, focusing starlight into one tight point. The precision of those adjustments was measured in tens of nanometers, tiny fractions of the width of a human hair. While that quiet work unfolded, outside attention turned to what made Webb different from Hubble in a more fundamental way than size or distance. Hubble, with its roughly 2.4-meter mirror, sees mainly invisible light and a bit into the ultraviolet and near-infrared. It shows us galaxies and nebulas as our eyes might see them if they were impossibly sensitive and floating above the atmosphere. Webb, with its mirror of about 6.5 meters across, was designed from the beginning as an infrared observatory. The reason lies in the way the universe stretches light. As space expands, wavelengths of photons traveling through it are stretched as well. Light that left a distant galaxy in the ultraviolet or visible bands will, after billions of years of travel through expanding space, arrive at our telescopes, shifted into the infrared. The more distant the galaxy, the more extreme the redshift. To see the first generations of galaxies, then, you must be able to see well into the infrared. If your telescope is blind to those wavelengths, those galaxies are effectively invisible, no matter how large your mirror. Infrared vision brings other advantages. Dust, which blocks and scatters visible light, becomes more transparent at longer wavelengths. Regions that look dark and opaque to Hubble can glow with structure in Webb's cameras. Star-forming clouds, planet-forming disks, the cores of galaxies swaddled in dust. All of these open up in the infrared like rooms behind curtains. In July of 2022, after months of cooling, alignment, and instrument commissioning, Webb released its first full set of images and spectra. July 12th marked the public start of its science operations. Behind each of those images was a chain of calibration files and algorithms, all tuned to turn raw data into something reliable. The moment the first deep field was shown, scientists knew that the telescope was not only working, but working at or beyond its promised performance. The mixture of emotions in the community was not simple joy. For years, Webb had been framed as an observatory that could not be allowed to fail. Its budget, its delays, its single point of launch meant that an early loss would ripple through the entire field of space-based astronomy. Now it had not failed. It had survived. It had opened its eye, and suddenly, the question was not whether the telescope would work, but whether cosmology itself was as stable as people had assumed. Outside the technical world, culture reached for metaphors. Some compared Webb's first images to scenes from the film Interstellar, released in 2014, with its meticulously rendered black hole and its play with time and gravity. There was something similar in the way Webb's pictures hinted at layers of time stacked along the line of sight. Except here, the glow and the arcs and the blurred tiny smudges were not computer graphics. They were the universe, as recorded by a machine far from Earth, stretched across wavelengths the human eye cannot see. Officially, Webb's science goals were plain and modest on paper. Study the first galaxies. Trace the formation of stars and planetary systems. Probe the atmospheres of exoplanets for chemical signatures. Provide high-resolution spectra of objects near and far. Each of those goals could fit neatly under the umbrella of understanding our cosmic origins. A prosperous slaughter, but there was a quieter aim beneath those bullet points. By pushing into regimes where models had less direct guidance, Webb would test the boundaries of the standard picture. If the lambda cold dark matter model was fully robust, the new data should thread into it smoothly. If there were cracks, Webb's sensitivity and depth might widen them. So out beyond the moon, a golden mirror cooled in permanent shadow, facing away from the sun, tethered only by radio waves and our expectations. It circled its invisible balance point, wrapped in a silver sunshield, its instruments humming softly in deep cold. It was not built to give us comforting confirmations. It was built to let us ask, what happens if we look, really look? Where our theories are thinnest? The first answer to that question did not arrive as a theory or a press release. It arrived as a single image. On July 11th, 2022, astronomers stood on a stage and showed the world what Webb had seen in a tiny patch of sky called SMACS 0723. It was presented as the deepest infrared view of the universe ever assembled at that time, and yet the region it covered on the sky was smaller than the apparent size of the moon. If you held out your arm and covered the moon with your thumb, the deep field would fit well within the nail. SMACS 0723 is not just a name, it is a massive cluster of galaxies, a knot of matter whose gravity is strong enough to bend the paths of light passing nearby. In general relativity, that bending turns clusters like this into lenses. They magnify and stretch the images of galaxies even farther behind them, galaxies that would otherwise be too faint to detect. By pointing Webb at such a cluster, astronomers were not just looking at one distant object, they were using the universe itself as an optical device. When the first full-resolution versions of that field appeared on screens, the effect was quiet but deep. At first glance, it looked like a scatter of colored points and smudges on a dark background, but as people zoomed in digitally, the structure began to reveal itself. Nearly every point of light, aside from a handful of foreground stars with telltale diffraction spikes, was a galaxy. Some were round, some elongated, some strangely stretched into thin arcs that curved around the center of the cluster. Those arcs were the most direct signatures of warped space-time in the image. Each one was a distant galaxy, its light deflected along curved paths by the mass of the cluster in front of it. In some cases, the same background galaxy appeared multiple times in different places, like echoes. You could trace the arcs with your eye and feel, in a way that went beyond equations. That space between those galaxies was not flat. The image itself was a map of gravity made visible. Astronomers did not just admire the picture. They began to measure it. They catalogued the shapes, colors, and brightnesses of the galaxies scattered across the field. Using filters that isolate different bands of infrared light, they built up crude spectra that hinted at each galaxy's distance. In this language, distance is often expressed not in light years but in redshift, a measure of how much the expansion of the universe has stretched the light. The higher the redshift, the earlier in cosmic history that light began its journey. What they found, as they probed deeper into the faint end of the image, surprised them. There were more tiny, faint, very distant galaxies at extremely high redshift than many models had predicted. Candidates began to appear with estimated redshifts greater than about 10, meaning we were seeing them as they were only a few 100 million years after the Big Bang. These were not just occasional outliers. They formed a small but noticeable population crowded into the early universe. To translate that into time, think of the universe's age as a long day. Seeing galaxies at redshift 10 or more is like looking back to the first hour or so after dawn, when the sky is still changing quickly from dark to light. The expectation had been that galaxies in that early interval should be small, relatively dim, and rare. The SMACS field and other early Webb deep fields that followed suggested something more intense. The early universe looked busier. As data poured in from SMACS 0, 7, 2, 3 and other fields, teams around the world rushed to analyze the numbers. In August and September of 2022, the first preprints appeared on RxIve claiming the detection of galaxies that seemed, on paper, almost implausibly massive for their age. Using Webb's photometry, they estimated the stellar masses of these objects and found values comparable to, or even larger than, the mass of the Milky Way, all within a few 100 million years of the universe's beginning. Headlines reached for striking phrases. Some called them universe breakers. Others suggested Webb was breaking cosmology. The core of the claim was simple enough. These galaxies look too bright, too big, too soon. Why is brightness such a problem? In very rough terms, the more stars a galaxy has, the more light it emits. There are complications, of course. Young, hot stars shine differently than older, cooler ones. Dust can absorb and re-emit light. But if you see a galaxy that is both extremely bright and apparently extremely distant, the straightforward interpretation is that it contains a large mass of stars that have already formed. In the standard picture of structure growth, there simply has not been enough time. By 300 or 400 million years after the Big Bang, for many galaxies of that scale to assemble, dark matter halos have to grow. Gas has to fall into them, cool, and fragment. Stars have to form in large numbers, without being blown back out by their own radiation and supernova explosions. To get to Milky Way-like masses that early, star formation would have to run in a kind of fast-forward mode, with very high efficiency, in halos that collapsed unusually quickly. The Hubble Ultra Deep Field, assembled in the early 2000s after hundreds of hours of exposure, had been our previous deepest optical and near-infrared view. It revealed galaxies out to redshifts of around 10. But the number and brightness of those most distant objects were limited by Hubble's smaller mirror and shorter wavelengths. Webb, with its larger mirror and infrared sensitivity, suddenly opened a new layer beyond that. The comparison is not a simple one-to-one, but the impression was clear. Where Hubble hinted, Webb counted. Still, the word impossible in those early discussions needed careful handling. The first estimates of distance and mass in the SMACS field, and others like it, were based largely on photometric redshifts. That means they were inferred from how bright a galaxy appears in different filters, rather than from precise spectroscopic measurements of individual emission or absorption lines. Photometric methods are powerful, but they are also vulnerable to confusion. Dust can redden a galaxy's light in ways that mimic greater distance. Certain combinations of stellar populations can produce similar colors at very different redshifts. In addition, the masses of those early galaxy candidates were not weighed directly. They were estimated by fitting models of stellar populations to the observed brightness and colors. Those models rely on assumptions about the initial mass function, the distribution of star masses when they form, and the history of star formation in the galaxy. Change those assumptions slightly, and the inferred mass can shift significantly. Then there is the lens itself. SMACS 0723, like other cluster lenses, magnifies background galaxies by factors that depend on their position and the detailed mass distribution of the cluster. If the magnification is underestimated, then the intrinsic brightness and mass of the background galaxy are overestimated. Building accurate lensing models is a complex task, and early versions can carry substantial uncertainties. All of these caveats became part of the discussion. Were some of the impossibly massive galaxies in fact less extreme, their redshifts overestimated because dusty, somewhat nearer galaxies can masquerade as very distant ones in photometry alone? Were lensing amplifications being handled consistently? Were modelers implicitly using assumptions tuned to later, more mature galaxies when fitting these very early systems? As spectroscopic follow-up began, some candidates had their redshifts revised downward. A few objects that had initially appeared to sit at redshift around 15 turned out to be nearer, their colors shaped by dust and strong emission lines rather than by extreme distance alone. Each such reclassification was a reminder of how easily preliminary data can seduce us into seeing crises where there are, instead, calibration issues. But the pattern did not disappear. Even after some of the most dramatic candidates were toned down, Webb's early results continued to show a larger-than-expected population of bright, compact galaxies at high redshifts. Even if their masses were not as high as the most breathless preprints had claimed, they still nudged against the comfortable borders of existing models. The early universe, within the first few 100 million years, seemed capable of organizing matter into luminous structures with surprising speed. The debate that unfolded over the following months was not a simple split between those who believed the data signaled new physics and those who dismissed it as error. Most astronomers lived somewhere in between. They recognized that measurement and interpretation were entangled. They also recognized that, even if every single candidate turned out to be less extreme than the first fits suggested, the fact that so many objects sat near the edge of expectations told them something important. It marked a region where their models were fragile. One of the key questions became not, are these galaxies truly impossible? But what would need to be true for them to be ordinary? Perhaps the efficiency of star formation in the early universe was higher than assumed. Perhaps the initial mass function was skewed toward more massive stars, making galaxies brighter for a given mass. Perhaps the simulations, with their finite resolution and simplified feedback recipes, undercount very rapid early bursts of star formation in rare halos. Or perhaps, in some quiet way, the underlying cosmological model would need tuning, not a dramatic overthrow of the Big Bang, but an adjustment to the way structure grows, or to the properties of dark matter, or to the behavior of dark energy at very early times. These possibilities remained speculative, and most researchers were cautious. Yet they floated in the background, part of the mental landscape as new data came in. For someone lying awake at night, listening to all this from a distance, the details of redshift estimation methods and stellar population synthesis might feel remote. But the emotional core of that early Webb era is easier to grasp. Imagine thinking that you know roughly how crowded a city should be at dawn, based on years of watching sunrise from a hill. Then one morning you lift a more powerful pair of binoculars and discover that, in the half-light, the streets are already far busier than you had ever imagined. People are moving quickly, lights are on, in more windows. The city has been awake for longer than you thought. Are we seeing truly impossible objects? Or are we seeing the limits of how we interpret new kinds of data, pushed to their edge? That is not a rhetorical question in science. It is a process. Each new spectrum, each refined lensing model, each update to simulation codes is part of the answer. Regardless of how the individual cases resolve, Webb has already done one irreversible thing. It dragged the boundary of the unknown closer to the beginning of time. Where once our most detailed observations comfortably started billions of years after the Big Bang, we now glimpse the universe, in its first 300 or 400 million years, with an intimacy that no previous telescope could offer. The questions that used to live in theory papers and simulation outputs now stare back at us as faint smudges of light, packed into patches of sky smaller than the moon. It is one thing to find a few bright knots in the first light of the cosmos. It is another to realize that, according to your best maps, many of them should hardly exist at all. When theorists and simulators looked at Webb's early galaxy counts, what unsettled them was not just the novelty, it was the statistics. In the standard picture, the lambda cold dark matter model, you can take what you know about the average density of matter in the universe, let gravity do its work in a computer, and watch structure grow from tiny ripples into a cosmic web. Small clumps appear first, then bigger ones, over billions of years. In those virtual universes, galaxies with masses similar to the Milky Way do emerge, but finding them very early in cosmic history is supposed to be rare, like rolling the same unlikely number on a die again and again. When Webb pointed at clusters like SMACS 0723 and at other deep fields without foreground lenses, it seemed to be finding not just a few bright early galaxies, but a surprising number of them. For the people who spend their lives running simulations of cosmic structure, that was a problem. Their codes had been tuned to match a wide range of observations. The distribution of galaxies nearby, the clustering patterns on large scales, the properties of galaxies at moderate redshifts. If the same framework now struggled to produce enough massive galaxies early on, something in the setup might be incomplete. At the heart of this is a simple idea with an invisible ingredient. Galaxies live inside dark matter halos. These halos are giant, roughly spherical clumps of dark matter, the unseen mass that outweighs all the stars and gas we can see. They form where gravity pulls dark matter together, and their growth over time sets the stage for everything else. Gas falls into the potential wells of these halos, cools, and eventually forms stars. No halo, no galaxy. To get a huge galaxy early in the universe, you need a massive dark matter halo to form early as well. That is difficult because, in the standard model, the biggest halos grow out of mergers of smaller ones. There is only so much time between the Big Bang and, say, 300 million years later. In simulations, halos massive enough to host Milky Way like galaxies do exist at those times, but they are extremely rare. Finding a handful might be acceptable. Finding many begins to strain the expected distribution. Even before Webb, there were hints that the early universe might be more active than naive expectations suggested. Deep surveys with Hubble and large ground-based telescopes had uncovered several bright galaxy candidates at redshifts around 8 to 10. Those discoveries prompted their own small debates. Were these objects truly as distant and luminous as they appeared? Or were selection effects, dust, and limited wavelength coverage distorting the picture? The data were thin, the error bars wide. Webb was, in many ways, built to settle those uncertainties. With its larger mirror and expanded infrared sensitivity, Webb could detect light from galaxies at even higher redshifts, and could take spectra that record detailed information about their composition and distance. As the first year of Webb observations unfolded, astronomers used those capabilities to check and refine their early candidate lists. At the same time, theorists reacted. In 2023 and 2024, a wave of papers appeared that revisited the assumptions baked into galaxy formation models. One major target was star formation efficiency. How much of the gas that falls into a halo actually turns into stars, and how quickly? In many simulations tuned to later epochs, this efficiency is moderate. Feedback from stars and black holes heats and expels gas, regulating growth. But perhaps, in the very early universe, conditions were different. The gas might have been denser, cooling more rapidly. Feedback might have been less effective at blowing material away. If star formation ran hotter for a brief period, galaxies could build up their stellar masses more quickly than standard recipes allow. Another focus was the initial mass function, the statistical distribution of star masses when they are born. In the nearby universe, observations suggest that stars tend to form with a characteristic pattern. Many low-mass stars, fewer intermediate mass ones, and very few extremely massive stars. But that pattern is based on environments rich in metals, in gas that has been recycled by previous generations of stars. In the pristine or nearly pristine conditions of the early universe, the gas chemistry and cooling channels are different. It is plausible that the first galaxies formed a larger fraction of high-mass stars. This idea becomes one of the patch hypotheses for the Webb tension. If early galaxies preferentially built massive stars, then per unit mass of stars, they would be brighter, especially in the ultraviolet and blue light that gets shifted into the infrared by cosmic expansion. Through Webb's eyes, they would look heavy. But their true stellar mass could be lower than inferred by models that assume a later universe initial mass function. They would still be impressive, but not quite as extraordinary as first estimates suggested. Dust content was another lever. The amount and properties of dust grains in these early galaxies affect how they absorb and re-emit starlight. Dust can make galaxies appear redder and dimmer in some bands, and brighter in others. Radiative transfer through dusty regions is complex, and the models used to interpret Webb data have to make assumptions about the size, distribution, and composition of grains. Adjust those, and the inferred masses and star formation rates can shift. Amid these theoretical adjustments, the story of particular galaxies illustrates how science prunes its own extremes. In the early rush of Webb analysis, some teams reported candidates with photometric redshifts around 13 or higher. If those distances were confirmed, the galaxies would be seen as they were only a little more than 300 million years after the Big Bang, with surprisingly high luminosities. They were quickly labeled as especially impossible. But as deeper spectroscopic observations were obtained, at least some of these extreme cases moved inward in time. Emission lines revealed that what had looked like a sharp break in the photometry, interpreted as the signature of very high redshift, was in fact shaped by strong features in the galaxy's spectrum at more moderate redshift, combined with dust effects. In other words, the galaxy was nearer, though still impressive. The miracle objects shrank back toward the edge of the possible. This is not a failure. It is the process working as intended. Photometric redshifts are quick sketches. Spectroscopic redshifts are careful portraits. When the latter correct the former, the field as a whole becomes more grounded. Extreme claims are filtered, not mocked. The lesson is not that the early, impossible headlines were foolish, but that early data, especially at the boundaries of detection, should always be held with an open hand. And yet, when you zoom out from the fate of individual candidates, a pattern remains. Even accounting for revised distances, for dust, for more careful lens modeling, Webb's census of early galaxies still leans toward more structure, more light, more apparent maturity than many baseline simulations predicted. It is as if the universe, in its first few 100 million years, was more efficient at turning primordial simplicity into complexity than we had assumed. To make that feeling more intuitive, it helps to borrow a metaphor from stories not about stars, but about people. In films and novels, there is a recurring character, the child who seems old before their time. They speak with an adult's insight. They carry themselves with a gravity that feels out of step with their years. Around such a child, the adults are forced to re-examine their own assumptions about what childhood should look like, how quickly a person can learn, how experience and temperament interact. Webb's early galaxies can feel like that. On paper, they belong to a young universe, only a small fraction of its current age. But their brightness, their compactness, their metal content in some cases, suggest that they have already raced through phases of growth that standard models spread out more gently. They are not necessarily contradictions. They are reminders that our sense of what young looks like is shaped by limited experience. Imagine, for a moment, that you could stand on a planet in one of those early galaxies. The sky above you would not match the calm canopy of stars we see now. The density of bright, massive stars would be higher. Their lifetimes, measured in only a few million years, would end in frequent supernovae. Explosions would pepper the sky on human timescales, leaving expanding shells of gas that glowed in different colors. The background might be laced with the faint haze of ionized gas, lit by the combined radiation of the first generations of stars. Night, in such a place, would be a noisier thing. Not necessarily louder in sound, but crowded in light. The idea of a quiet cosmos, with occasional rare supernovae and a stable set of constellations, would make little sense. The universe would feel like a city in the middle of a growth spurt. Cranes and construction everywhere, no corner truly at rest. When theorists run their simulations and find that such rapid assembly of luminous galaxies is unlikely under default assumptions, they do not automatically throw out the whole framework. Instead, they start asking layered questions. How many of these galaxies can be explained as ordinary statistical fluctuations, the rare peaks you expect when you have many chances? How much of the apparent excess is due to selection bias, to our tendency to publish and pay attention to the most extreme cases? How much can lensing magnification and its uncertainties be shaping our sample? What happens if we let star formation be temporarily more efficient in certain conditions? As those questions are explored, some of the tension relaxes. Perhaps the universe is not quite as dramatically overproductive as the first headlines suggested, but the unease does not vanish entirely. Even conservative analyses often conclude that, compared to older expectations, there is more early structure than the simplest models anticipated. More small galaxies, more intermediate ones, more light. The impossible thing here, in the end, is not one galaxy whose details might turn out to be mismeasured. It is the collective impression. A young universe that seems, in multiple independent observations, to have done more work, more quickly than our cleanest pictures allowed. Like noticing that many of the children in a classroom are reading far beyond their grade level, you begin to suspect that there is something about the environment, or your grading system, that needs updating. The cosmos is not misbehaving. It is simply more vigorous, more impatient with our timelines than we were ready to admit. The sense that the universe rushed its own childhood does not end with how quickly galaxies came together. It deepens when you look inside those galaxies and realize how many stars must have lived and died to make them what they are. For a galaxy to look mature, to carry the fingerprints of heavy elements in its light, something has to have happened many times over. Clouds of pristine gas need to collapse into stars. The most massive of those stars must burn fiercely, fuse light elements into heavier ones, and then die in explosions that scatter those elements back into space. New stars then form out of that enriched gas, inheriting those heavier atoms. That cycle, birth and death and rebirth, is not instant. It takes time. Astronomers use a simple word for all elements heavier than helium: metals. Carbon, oxygen, nitrogen, silicon, iron. All of them count as metals in this language. It is a rough label, but it points to something important. Metals are made in stars. Their presence is a record of stellar generations. The more metals you see in a galaxy's gas and stars, the more times that galaxy has gone through the cycle of star formation and death. In that sense, metals are timestamps, not in the way a clock stamps a moment, but in the way rings in a tree trunk trace seasons. When Webb takes a spectrum of a distant galaxy and finds strong signatures of oxygen or carbon, it is seeing the ashes of previous stars. If those signatures appear very early in the universe's history, they whisper that more cycles have occurred in a short window than simple models expect. Some of Webb's spectra of high redshift galaxies show exactly that. Bright emission from ionized oxygen, traces of carbon, in some cases, hints of dust, those tiny solid grains made largely of heavier elements and often associated with the debris of dying stars. These are not just pretty details, they are direct evidence that, by the time we are looking at them, the galaxies have already been through significant chemical evolution. And yet, the cosmic clock at those redshifts is restrictive. When we look at galaxies in the first few 100 million years after the Big Bang, we are peering into an era when the universe has not had much time to recycle its material. There is a limited number of generations of massive stars that can have formed and died. Seeing what looks like a chemically seasoned galaxy in such an early frame is like walking into a house only just built and finding the walls already worn smooth by decades of hands. Before Webb, other telescopes had already hinted that the young universe might not be as chemically simple as theory once imagined. The Spitzer Space Telescope, with its infrared cameras, picked up excess light in certain bands from very distant galaxies. Those excesses were interpreted as the glow of strong emission lines from oxygen and hydrogen, implying that even at redshifts near 8 or higher, galaxies contained gas enriched by previous stars. Hubble, working at the edge of its infrared vision, contributed additional clues by charting the colors of early galaxies, which suggested some level of metal content and dust. But both Spitzer and Hubble were limited. Their spectral resolution and wavelength coverage made it difficult to disentangle overlapping features. The picture they painted was suggestive, not sharp. Webb's infrared spectrographs changed that. By spreading the light of a distant galaxy into a detailed rainbow over a range of wavelengths tailored to these questions, Webb could pick out individual emission lines from specific elements and ionization states. It could, for the first time on a large scale, measure the chemical fingerprints of galaxies in the era when the universe was just emerging from its initial darkness. Those measurements deepen the puzzle. If metals are timestamps, and if those stamps appear more numerous and elaborate than expected in very early galaxies, then either the cycles of star birth and death ran faster, or our sense of how many cycles should fit into that cosmic window is off. One way to reconcile this is to imagine that the first generations of stars were not like the stars we know best. Theoretical work going back decades has suggested that the very first generation of stars, often called Population 3, formed out of gas that contained no metals at all. Without those heavier elements to help gas cool and fragment, the physics of collapse changes. In many simulations, metal-free gas tends to form more massive stars, some with tens or even hundreds of times the mass of the Sunday. Massive stars live fast and die young. They burn through their fuel quickly, shining fiercely for only a few million years before collapsing into remnants or exploding as supernovae. A population of such stars would be a powerful engine for chemical enrichment. In a relatively short stretch of cosmic time, they could seed their surroundings with heavy elements, enabling subsequent generations of more ordinary, lower-mass stars to form in enriched gas. In that picture, the early universe does not enrich itself through a slow drip of metals over vast spans of time. It experiences something closer to a cascade. A wave of very massive, short-lived stars sweeps through, detonating one after another, enriching the gas rapidly. If Webb is now seeing galaxies lit by the descendants of that wave, their apparently advanced chemical state at young ages becomes easier to understand. But this remains, so far, an elegant possibility more than a directly observed fact. Even deep into the middle of the 2020s, Population 3 stars themselves have not been seen in isolation. They are expected to be too fleeting and, individually, too faint at the distances involved. Instead, astronomers look for indirect signatures. Particular patterns in the abundances of elements in extremely metal-poor stars in our own galaxy, for example, can hint that those stars were born from gas, enriched by one or a few earlier supernovae with unusual yields. With Webb, the hope is to catch the collective signature of such early, massive stars in distant galaxies. One of the key targets is a type of spectral line associated with helium that is very difficult to produce with ordinary stellar populations, but can be strong in gas lit by very hot, very massive stars. Astronomers look for that line, and for combinations of other features that, together, would point toward an underlying population of stars more extreme than anything in the nearby universe. Teams have combed Webb spectra of faint, high redshift galaxies for those telltale features. They have found intriguing cases, objects whose spectra show unusually strong high-energy emission lines, or line ratios that suggest extreme conditions. Some have been touted as possible sites where population 3 stars once dominated, but so far, a single, unambiguous smoking gun remains out of reach. Other explanations, such as compact star-forming regions with unusually hot but still metal-enriched stars, or the influence of growing black holes, can often fit the data as well. This uncertainty keeps the story open. It also illustrates the way science handles the word impossible. The lack of a clean detection does not erase the need for some mechanism to explain rapid early enrichment. Instead, it sharpens the questions. Were the first stars as massive as some theories suggest, or only somewhat more massive than average? Did they form in short, intense bursts, or in a more continuous way? How much of Webb's observed metal content can be accounted for by known population types if we push their parameters? And where do we hit real limits? When you watch a film like Interstellar, dying stars and black holes serve as dramatic backgrounds for human stories. They are stage pieces and symbols. On Webb's screens, the birth and death of stars are not decorations. They are the gears of the cosmic clock. How quickly they turn, how violently they spin, determines how rapidly the universe moves from simple to complex. If massive early stars were more common than in later times, then many galaxies would have raced through chemical childhood. Gravitationally bound gas clouds would light up with short-lived beacons that quickly seeded their surroundings with metals. Dust would begin to form in the cooling ejecta of supernovae and in the winds of evolved stars. That dust, in turn, would alter the way light travels, making galaxies appear redder, softening their glow, and providing the raw material for future planets. On the other hand, if the initial generations of stars were not dramatically different, then the early presence of metals and dust in Webb's spectra may be telling us something deeper about time itself in our models. Perhaps the way we convert between redshift and age in certain cosmological frameworks needs subtle adjustment. Perhaps the average rates we assume for star formation and feedback undercount short, intense episodes in rare environments. In that case, the issue is not that the universe has done something impossible, but that we have smoothed over the jaggedness of its history. Either way, the stakes are high. The connection between time, star formation, and chemical enrichment sits near the foundation of modern astrophysics. It affects how we interpret the colors of distant galaxies, how we estimate their ages, how we reconstruct the timeline of reionization, the era when ultraviolet light from the first luminous objects stripped electrons from hydrogen gas and changed the transparency of the cosmos. Webb's data do not yet deliver a verdict. They add weight to the impression that some parts of the early universe grew up quickly, chemically speaking. They show spectra with oxygen and carbon, and hints of dust at times when, not long ago, many imagined mostly pristine gas. They make it harder to hold onto a picture in which the early cosmos is a simple, metal-free canvas gradually speckled with complexity. There is a quiet irony in this. For years, the phrase "young universe" conjured images of smoothness and purity. Now, the more closely we look, the more that youth resembles a kind of concentrated aging. Stars blazing and burning out, elements synthesized and scattered, dust condensing and reshaping the light. Not a long, slow march, but a series of rushes. Maybe the universe was younger than we think, not in the count of years, but in how quickly it learned to grow old. Nothing embodies that compressed aging more starkly than the places where time itself seems to fold. At the centers of some early galaxies, gravity did not just hurry, it sprinted. Long before Webb flew, astronomers had already known that the distant universe hosts quasars, points of light so bright that for a moment they outshine entire galaxies. These are powered by supermassive black holes, monsters with masses of hundreds of millions or even billions of suns, swallowing gas in violent spirals and converting some of that infall into radiation. Surveys like the Sloan Digital Sky Survey, scanning wide swaths of the sky, found quasars at redshifts greater than about 6 or 7. That means we see them as they were when the universe was less than 1 billion years old. Even without Webb, those discoveries carried a quiet puzzle. A black hole that weighs billions of solar masses does not appear from nowhere. In the simplest story, it starts as a much smaller seed, perhaps the collapsed core of a massive star, a few tens of solar masses, or a black hole formed in the dense chaos of a star cluster. From there, it can grow by merging with other black holes and by accreting gas. But both of those processes take time. There is a natural speed limit on black hole growth known as the Eddington limit. If gas falls in too quickly, the radiation emitted as it heats up pushes back on the inflowing material, resisting further accretion. A black hole can get around this limit briefly if the geometry is just right, or if it swallows dense clumps. But to sustain rates above that limit for long is difficult in standard models. When you work through the math, starting from a seed of a few tens of solar masses and letting it grow at or below the Eddington limit, you find that reaching billions of solar masses in less than 1 billion years is challenging, not impossible in a strict sense, but requiring growth near the maximum allowed rate, almost continuously. The quasars found by Sloan and similar surveys sat right in that uncomfortable zone. Their existence told astronomers that, somehow, in the first few 100 million years, black hole seeds had formed and then grown extraordinarily quickly. But the observations from that era had limits. The host galaxies around those quasars were hard to resolve. The environments, the detailed distribution of gas and stars in the surrounding regions, were blurry. The black holes were like bright headlights in a fog. You could see that they were there. You could not easily make out the street they were driving down. Webb, with its infrared vision, offers more than just detection. It can probe the structure around those distant quasars, separating light from the accretion disk and from the host galaxy, mapping how gas and stars are arranged in their neighborhoods. Combined with radio and submillimeter observatories, it allows astronomers to build a more complete picture of the fuel supply that feeds those early black holes. The growth problem remains. Imagine you plant a seed barely larger than a pebble and, by the time a single season has passed, you find a tree tall enough to tower over a city. You would suspect that either the seed was not as small as you thought, or that the conditions for growth were far more favorable than any you have seen before. For supermassive black holes in the early universe, both possibilities are on the table. One influential idea proposes that, instead of forming from the corpses of ordinary massive stars, some black holes were born big. In certain rare pockets of the early universe, gas clouds might have collapsed directly into black holes with masses of tens of thousands to perhaps 1 million suns. These are called direct collapse black holes. The conditions for such a collapse are specific. The gas must be hot and dense, but somehow prevented from fragmenting into many smaller stars. Radiation from nearby star-forming regions might help by keeping the gas warm and suppressing cooling channels that would otherwise break the cloud into pieces. If direct collapse happens, the starting point for growth changes dramatically. A black hole that begins life with, say, 100,000 solar masses has far less distance to travel in growth space to reach the billion solar mass scale by the time we observe it at high redshift. It still needs gas to feed on, and it still wrestles with the Eddington limit. But the timeline is less strained. Instead of a pebble becoming a skyscraper tree, you begin with a sapling already high as a house. Webb and other observatories have started to find hints that the environments around some very distant quasars are exactly the kind that direct collapse models imagine. Dense reservoirs of cold gas, compact, turbulent galactic cores, where inflows along cosmic filaments may continuously deliver new material, signs that star formation and black hole feeding are intertwined. With the central regions of these early galaxies acting as both nurseries and engines. In some cases, Webb's spectra reveal broad emission lines from gas swirling close to the black hole, indicating high accretion rates, alongside narrow lines from gas farther out, tracing the structure of the host galaxy. The combination suggests not a lonely black hole in a faint halo, but a complex, fuel-rich system, where gravity and radiation are locked in a feedback dance. Gas flows in, heats, shines, and in some directions is driven back out in winds. For the wider public, these details rarely make headlines. What does break through are phrases like "too big, too early." Popular science articles pick up the technical discomfort and translate it. They talk about black holes in the infant universe that seem, at first glance, too massive for their age. They quote researchers who admit, carefully, that these observations put pressure on existing models. The crisis is not that black holes exist, it is that their biographies feel compressed. In fictional universes, black holes often serve as gateways. In 2001, A Space Odyssey, a journey beyond Jupiter and into a mysterious portal marks a leap in consciousness, a rupture in ordinary time. In many stories, a black hole or a wormhole is the place where narrative structure bends, where characters skip ahead in understanding or are thrown into a future they did not expect. With Webb's data, early supermassive black holes take on a related but quieter symbolic role. They represent leaps in structure, places where the universe seems to have skipped grades. You expect, on the basis of your simulations, that galaxies and their central black holes should pass through certain stages in order. Small halos, small black holes, modest accretion, then gradual growth. More stars, more gas, larger halos. To find a billion solar mass black hole, less than a billion years after the Big Bang, is like finding a child in a classroom who has somehow aged decades ahead of schedule in just a few months. The scientific questions that follow are specific but have a common thread. Do we need to revise the physics of how black holes accrete gas at high redshift? Are there regimes where super-Eddington accretion, sustained growth above the usual limit, is more common than current models allow? Are we underestimating the number or the mass of black hole seeds, perhaps by missing crucial formation channels like dense stellar clusters collapsing into single objects? Or is there something about the environments of the early universe, with higher average densities and more rapid inflows, that changes the rules? Feedback, the way a growing black hole influences its surroundings, is also under scrutiny. In many galaxy formation simulations, feedback from active black holes helps regulate star formation. Jets and winds heat and expel gas, preventing a runaway spiral of growth. But if that feedback is weaker or differently directed in early galaxies, black holes might be able to gorge more freely for a while, growing faster than the average prescriptions predict. Webb's role in this story is not to deliver instant answers. It is to resolve the scenes in more detail, to show astronomers whether the hosts of early quasars are isolated or embedded in rich protoclusters, to map how gas flows along filaments into the centers of those structures, to measure the metallicity of gas near the black hole, which can reveal how many generations of stars have already lived and died there, to look for correlations between black hole mass and galaxy mass at times when both are still in the act of building themselves. All of this folds back into the larger question that runs through the Webb era. How much of what we see as too fast or too massive is a sign that physics is incomplete, and how much is a sign that we have smoothed over the universe's natural capacity for bursts and extremes? Real histories are rarely linear. They are often punctuated by episodes of rapid change followed by quieter stretches. Even if direct collapse black holes turn out to be common, and even if some early quasars can be explained by a combination of favorable initial conditions and temporarily elevated accretion, the feeling that these objects compress time remains. A supermassive black hole in the early universe is not just a heavy object. It is a record of how effectively gravity, gas dynamics, and radiation conspired to turn diffuse matter into something concentrated and persistent. We sometimes talk about black holes as if they are the end of a story. Matter falls in and, from our perspective, vanishes. What Webb reveals is that In the early universe, these objects are also beginnings. They anchor the centers of galaxies. They influence how stars form around them. They carve out channels in gas and heat their surroundings. Their mass, their presence, shapes the future of the structures in which they sit. To say that the impossible thing is not the black holes themselves, but their compressed history, is to focus on the right unease. A 5-year-old with the body of a 50-year-old would be an affront not to biology, but to our sense of time and development. In the same way, a billion solar mass black hole in a universe still counting its age in hundreds of millions of years challenges our intuition about how growth should unfold. Black holes already win against matter. They capture light, twist space-time, and sit at the centers of galaxies like anchors that nothing can move. Now, in Webb's portraits of the young cosmos, they seem to be winning against another thing we thought we understood: the pace at which the universe is allowed to evolve. They are not just eating gas and stars. In some quiet, unsettling way, they are eating the evolutionary time we had assigned to them. If some parts of the cosmos have been racing through their own histories, then another realization follows quietly in the background. They have been doing all of this not in a sparse, lonely universe, but in a crowd. Long before Webb, astronomers already knew that the observable universe contained an astonishing number of galaxies. The first Hubble deep fields, stitched together from days of staring at apparently empty sky, became the basis for one of the most quoted facts in modern cosmology. There are at least hundreds of billions of galaxies within the part of the universe we can see. For most of us, that sentence alone is already more than the mind knows how to hold. Those estimates do not come from a cosmic census taken one by one. They are built from small windows. You count how many galaxies appear in a deep field image, a tiny patch of sky. You correct for the ones that are too faint even for Hubble to see, using models of how brightness is distributed. Then you scale that number up to the whole sky, like taking the density of trees in one forest clearing and applying it to an entire continent. It is a careful extrapolation, with error bars and caveats, but the broad conclusion is stable. The night is thick with islands of stars. Even before Webb launched, some astronomers suspected that the true number might be higher than those early estimates. Analyses in the 2010s and early 2020s, combining Hubble deep fields with models of galaxy formation, suggested that if you include the smallest, faintest galaxies that even Hubble could not resolve, the total count might reach into the realm of 1 or 2 trillion. Many of those galaxies would be tiny compared to giants like the Milky Way, fragile systems easily disrupted. But they would still be galaxies, bound collections of stars, gas, and dark matter, each with its own small history. Webb's arrival did not fundamentally change the way these numbers are derived. It changed the input. With its deeper infrared sensitivity, Webb can detect galaxies that are both more distant and intrinsically fainter than what Hubble could reach. It sees small systems at high redshift that were effectively invisible before. In doing so, it fills in pieces of the faint end of the galaxy population, especially in the early universe. When you look at a Webb deep field, and then at the catalogs built from it, you find that the sky is denser than human intuition once assumed. Every additional faint smudge that turns out to be a galaxy, every tiny, high redshift object that adds to the count, nudges the statistical estimates upward. The exact number will always carry uncertainties, but the trend points in one direction. The more sensitive our telescopes become, the more galaxies we see. To make this less abstract, imagine standing under a perfectly dark sky, somewhere far from city lights. Now adjust your imagination. Instead of stars, suppose every point of light you see is a galaxy, and not just the bright ones you can find with the naked eye, but layer upon layer of fainter galaxies behind them, stacked along the line of sight. In almost any direction you glance, there would be not dozens, not hundreds, but thousands of galaxies overlapping in your view, each at a different distance, each emitting its own light that left long before you were born. What Webb does when it stares into a small patch of sky is to approximate that impossible view. Its images condense that layered density into a frame you can look at on a screen. Yet even those pictures are modest. Posters and wallpapers built from Hubble or Webb deep fields often show a few dozen prominent galaxies, spaced out in a way that is aesthetically pleasing and not too overwhelming. That is a human choice. In reality, the universe is not composed for our comfort. It is overfull. The difference between what we display and what is actually out there mirrors a deeper tension. Our brains are built to handle small numbers, familiar scales, a handful of people, a village, a city. Once numbers reach into the territory of hundreds of billions or trillions, they no longer feel like quantities. They become flavors of the same incomprehensible vastness. Hearing that there are a few 100 billion galaxies versus 1 or 2 trillion does not feel viscerally different. And yet, on paper, it is. So, there is a psychological question hiding inside a technical one. When you hear that the observable universe may hold trillions of galaxies, what happens inside you? Do you feel smaller, more anonymous, as if you live in an endless metropolis where individual stories lose their weight? Or does it feel more like discovering that your hometown is part of a larger, bustling world, with more neighborhoods and cultures than you had guessed? Astronomers themselves have had to adjust their intuition. Picture a researcher in the mid-1990s seeing the first Hubble Deep Field appear on a monitor. For them, that image was a revelation. Thousands of galaxies in a patch of sky so small you could cover it with a grain of sand held at arm's length. It stretched their sense of cosmic density. It changed how they thought about the richness of the universe. Now imagine a scientist in the early 2020s looking at a Webb deep field. The basic kind of image is the same, a crowded frame of galaxies. But the depth is different. The colors are mapped from infrared, reaching to wavelengths that the earlier telescope could not access. The faintest smudges go deeper in time, closer to the first luminous structures. The sense of density is not only horizontal, spread across the sky, but vertical. In time, you are not just seeing many galaxies. You are seeing them layered across epochs, some already old, some just freshly lit. The raw pixel count of galaxies in the image is not what matters most. It is the way those images and the statistics derived from them force us to accept a scale that no instinct prepared us for. The impossible thing here is not a violation of physical law. It is a violation of our built-in expectations. Human minds did not evolve to deal comfortably with 10 to the 11 or 10 to the 12 of anything, let alone separate, living systems of stars and planets. And yet, that is the reality Webb points to. There is a quiet irony in how quickly we normalize it. Once the phrase hundreds of billions of galaxies entered popular science writing, it became almost a cliché, something you might hear in a documentary voiceover and file away as background noise. Adding a factor of 10 or more, by including the faintest systems, does not trigger a new emotional reaction. The numbers are too large for that. What Webb does, instead, is to peel back layers of ignorance at the low mass, high redshift end, where the difference between missing and seeing a population changes our understanding of how structure builds. In the context of Webb's other impossible findings, this crowdedness matters. A universe with more small galaxies early on is a universe with more sites of star formation, more places where metals and dust can be forged, more potential seeds for later mergers and growth. It reinforces the idea that the cosmos did not waste its early time. It used it, everywhere, all at once, in a way that our earlier observations had only partially captured. There is also a certain comfort in knowing that our Milky Way is not a rare jewel in a mostly empty case, but one of many billions of comparable systems, nested inside a lattice of even more numerous small galaxies. It suggests that whatever processes led to stars and planets, and perhaps life here, have had many other stages on which to play out, even if we will never see most of them. As you lie wherever you are, listening, the scale does not change. Your body remains the same size. Your room, your street, the familiar distances of your daily life do not expand. And yet, above the ceiling, beyond the atmosphere, photons from trillions of galaxies are still falling into Webb's mirror, into other telescopes, into the darkness. A rain of light that has been traveling for millions and billions of years, crossing an ocean of space we can describe but never truly imagine. We have only just learned to give that rain a name. Learning its names is one kind of boundary. Discovering where those names can never reach is another. When cosmologists talk about the universe, they sometimes mean two different things at once. There is the universe we can, in principle, observe, and there is the universe as a whole, which may be far larger, perhaps even infinite. The difference between them is not philosophical, it is set by light and time. The observable universe is defined by how far light has been able to travel since the Big Bang. In round terms, the universe has been expanding and cooling for about 13.8 billion years. That is how long light has had to move, carrying information from distant regions to us. But because space itself has been stretching during that time, the distance to the most distant galaxies we can see today is much larger than the simple product of speed and time. The diameter of the observable universe, measured in the present, is now on the order of 93 billion light-years. Those numbers sound neat, almost like the size of a room given in meters. But they hide a subtlety. There is no physical shell at that radius. No glowing bubble. No wall. The observable universe is not a container with an edge. It is a sphere of reachability. Inside it are all the places from which light has had time to arrive here since the beginning. Outside it are regions whose light is still on the way, or will never reach us at all. The term observable universe appears in textbooks and documentaries. It is drawn in diagrams as a circle or sphere around a small dot labeled us. And yet, for many people, the instinct is still to imagine a kind of edge out there, a border you could, in principle, fly to, a frontier where space ends and something else begins. Our everyday experience supplies no good metaphor for an expanding, horizon-bounded volume embedded in something larger and perhaps unending. Webb cannot change that instinct directly. What it can do is sharpen our sense of where our horizon sits in time. By looking at galaxies whose light has taken more than 13 billion years to reach us, Webb brings us close to the limit of what is observable. The deep fields and high redshift targets it studies live not just far away in space, but early in cosmic history. When you see them, you are looking along a ray that nearly grazes the edge of our light cone. That edge is set by causality as much as by light. Information, in general relativity, cannot travel faster than light. That means any event beyond our observable horizon is not just unseen, it is disconnected, in a strict physical sense. No signal from there can ever reach here, given the way the universe expands. The horizon is a boundary of possible influence. The discovery that the universe's expansion is accelerating made this picture stranger. In 1998, the supernova studies that revealed dark energy also implied that, as time goes on, more and more galaxies will cross beyond our future horizon. Their light, even if it is still reaching us now, will one day be stretched so extremely and weakened so much that it will no longer be detectable. For distant future observers, the universe will appear emptier. Structures that we see today will have slipped out of their causal world forever. The Nobel Prize in Physics, awarded in 2011 to the leaders of those supernova teams, was, in a way, a cultural marker for this new cosmic geography. It signaled that the idea of an accelerating universe, dominated by some form of dark energy, had moved from a surprising result to part of the shared framework. The textbooks updated, diagrams changed, the circle of the observable universe was now drawn in a space-time diagram where light paths bend differently and where future horizons exist even if space itself is infinite. Webb steps into this already strange landscape with a specific role. By observing certain kinds of stars and galaxies in the infrared, it helps refine our measurements of cosmic expansion across time. It adds anchoring points for the distance ladder, and it provides new ways to connect the behavior of the universe at early times, as seen in the cosmic microwave background, to its behavior at later times, as seen in galaxies and supernovae. By the middle of the 2020s, detailed reviews of what is often called the Hubble tension made it clear that a discrepancy persists. Measurements of the current expansion rate based on the early universe, especially those inferred from the microwave background, combined with the standard cosmological model, give a value around the high 60s in kilometers per second per megaparsec. Local measurements, based on Cepheid variable stars and type Ia supernovae in nearby galaxies, tend to give a higher number, around the low 70s. Webb, observing Cepheids and other distance indicators in the infrared, where dust interference is reduced, has offered a new check on some of the local measurements. Instead of erasing the difference, its data so far tend to support the higher local value. The split between early universe and late universe methods does not vanish. It becomes harder to blame entirely on simple measurement mistakes. This tension is not directly about the size of the observable universe, but it touches on the same boundary. The rate of expansion helps determine how fast the horizon grows, how quickly distant galaxies cross from the realm of the observable into permanent exile. If the expansion history of the universe is more complex than the simplest models assume, then our mapping from redshift to distance and time needs adjustment. Horizons may have different shapes than our first diagrams drew. Trying to picture all of this is difficult. One way to soften it is to think of the cosmic horizon as similar to the sea horizon. When you stand on a shore and look out, there is a line where the water seems to end and the sky begins. Sail beyond that, and a new horizon appears around you. The old shore drops out of view. Nothing in the ocean itself marks that line. It is defined by your position and the curvature of the Earth. The cosmic horizon is like that, but stranger. It is not just about what your eyes can see with their own limits. It is about what any signal could ever connect, given the speeds allowed in this universe and the way space stretches. Move to a galaxy millions of light years away, and your observable universe shifts with you. Some regions become visible that were not before. Others drop out of reach. There is no single absolute view. There are overlapping bubbles of knowable reality, each centered on an observer. Science fiction has long loved the image of the final boundary. The Edge of Space in 2001, A Space Odyssey, the event horizon of the black hole in Interstellar, the glowing barrier you approach and cross in order to enter a different regime of reality. Those images are sharp, dramatic, a threshold you can stand before and decide whether to step through. What Webb gives us is less theatrical and more austere. It confirms that there is a boundary, but not one we can ever touch. It is not a glowing wall in the distance. It is a limit in the equations that govern which events can affect which others. We can chart its location in space-time diagrams. We can calculate how it changes over time, but we cannot send a probe to it or stand there and look back. If there are galaxies beyond our horizon, and there almost certainly are, their stories are sealed off from us, not by distance alone, but by principle. If there are civilizations in those galaxies, they will never receive our signals. We will never receive theirs. The question, are we alone, becomes more layered in that light. Are we alone in our observable patch? In the whole universe? The second question may be meaningful in mathematics. In practice, we can only ever answer the first. Does that make the idea gentler or more frightening? On one hand, it limits the scale of our potential loneliness. We do not have to imagine being the only life in an infinite expanse, only in a bubble defined by light and time. On the other hand, it sharpens the sense that there might be countless other islands of awareness, forever invisible, whose existence we can theorize but never confirm. The impossible thing here is not that the universe lacks an edge. It is that parts of it are unreachable in principle, not just in practice. There are regions whose light will never touch us, whose histories will run their course without ever intersecting our own. They are as real, in a physical sense, as the galaxies we see in Webb's deep fields. But they will remain, to us, abstractions. Learning to live with that is its own kind of cosmological maturity. To accept that our instruments, no matter how powerful, will always paint an incomplete picture. To know that some stories in the universe will never appear in any dataset we collect. And yet, to keep watching. To keep listening to the light that does reach us from near the edge of what is possible. Knowing that beyond that line, the rest of the universe continues on, indifferent to our horizon. Learning its names is one kind of boundary. Discovering where those names can never reach is another. When cosmologists talk about the universe, they sometimes mean two different things at once. There is the universe we can, in principle, observe, and there is the universe as a whole, which may be far larger, perhaps even infinite. The difference between them is not philosophical. It is set by light and time. The observable universe is defined by how far light has been able to travel since the Big Bang. In round terms, the universe has been expanding and cooling for about 13.8 billion years. That is how long light has had to move, carrying information from distant regions to us. But because space itself has been stretching during that time, the distance to the most distant galaxies we can see today is much larger than the simple product of speed and time. The diameter of the observable universe, measured in the present, is now on the order of 93 billion light-years. Those numbers sound neat, almost like the size of a room given in meters, but they hide a subtlety. There is no physical shell at that radius. No glowing bubble. No wall. The observable universe is not a container with an edge. It is a sphere of reachability. Inside it are all the places from which light has had time to arrive here since the beginning. Outside it are regions whose light is still on the way, or will never reach us at all. The term observable universe appears in textbooks and documentaries. It is drawn in diagrams as a circle or sphere around a small dot labeled us. And yet, for many people, the instinct is still to imagine a kind of edge out there. A border you could, in principle, fly to. A frontier where space ends and something else begins. Our everyday experience supplies no good metaphor for an expanding, horizon-bounded volume embedded in something larger and perhaps unending. Webb cannot change that instinct directly. What it can do is sharpen our sense of where our horizon sits in time. By looking at galaxies whose light has taken more than 13 billion years to reach us, Webb brings us close to the limit of what is observable. The deep fields and high redshift targets it studies live not just far away in space, but early in cosmic history. When you see them, you are looking along a ray that nearly grazes the edge of our light cone. That edge is set by causality as much as by light. Information, in general relativity, cannot travel faster than light. That means any event beyond our observable horizon is not just unseen, it is disconnected in a strict physical sense. No signal from there can ever reach here, given the way the universe expands. The horizon is a boundary of possible influence. The discovery that the universe's expansion is accelerating made this picture stranger. In 1998, the supernova studies that revealed dark energy also implied that, as time goes on, more and more galaxies will cross beyond our future horizon. Their light, even if it is still reaching us now, will one day be stretched so extremely and weakened so much that it will no longer be detectable. For distant future observers, the universe will appear emptier. Structures that we see today will have slipped out of their causal world forever. The Nobel Prize in Physics awarded in 2011 to the leaders of those supernova teams was, in a way, a cultural marker for this new cosmic geography. It signaled that the idea of an accelerating universe, dominated by some form of dark energy, had moved from a surprising result to part of the shared framework. The textbooks updated. Diagrams changed. The circle of the observable universe was now drawn in a space-time diagram where light paths bend differently and where future horizons exist, even if space itself is infinite. Webb steps into this already strange landscape with a specific role. By observing certain kinds of stars and galaxies in the infrared, it helps refine our measurements of cosmic expansion across time. It adds anchoring points for the distance ladder, and it provides new ways to connect the behavior of the universe at early times, as seen in the cosmic microwave background, to its behavior at later times, as seen in galaxies and supernovae. By the middle of the 2020s, detailed reviews of what is often called the Hubble tension made it clear that a discrepancy persists. Measurements of the current expansion rate based on the early universe, especially those inferred from the microwave background combined with the standard cosmological model, give a value around the high 60s in kilometers per second per megaparsec. Local measurements, based on Cepheid variable stars and type Ia supernovae in nearby galaxies, tend to give a higher number, around the low 70s. Webb, observing Cepheids and other distance indicators in the infrared, where dust interference is reduced, has offered a new check on some of the local measurements. Instead of erasing the difference, its data so far tend to support the higher local value. The split between early universe and late universe methods does not vanish. It becomes harder to blame entirely on simple measurement mistakes. This tension is not directly about the size of the observable universe, but it touches on the same boundary. The rate of expansion helps determine how fast the horizon grows, how quickly distant galaxies cross from the realm of the observable into permanent exile. If the expansion history of the universe is more complex than the simplest models assume, then our mapping from redshift to distance and time needs adjustment. Horizons may have different shapes than our first diagrams drew. Trying to picture all of this is difficult. One way to soften it is to think of the cosmic horizon as similar to the sea horizon. When you stand on a shore and look out, there is a line where the water seems to end and the sky begins. Sail beyond that, and a new horizon appears around you. The old shore drops out of view. Nothing in the ocean itself marks that line. It is defined by your position and the curvature of the Earth. The cosmic horizon is like that, but stranger. It is not just about what your eyes can see with their own limits. It is about what any signal could ever connect, given the speeds allowed in this universe, and the way space stretches. Move to a galaxy millions of light years away, and your observable universe shifts with you. Some regions become visible that were not before, others drop out of reach. There is no single, absolute view. There are overlapping bubbles of knowable reality, each centered on an observer. Science fiction has long loved the image of the final boundary. The Edge of Space in 2001. A Space Odyssey. The event horizon of the black hole in Interstellar. The glowing barrier you approach and cross in order to enter a different regime of reality. Those images are sharp, dramatic, a threshold you can stand before and decide whether to step through. What Webb gives us is less theatrical and more austere. It confirms that there is a boundary, but not one we can ever touch. It is not a glowing wall in the distance. It is a limit in the equations that govern which events can affect which others. We can chart its location in space-time diagrams. We can calculate how it changes over time, but we cannot send a probe to it or stand there and look back. If there are galaxies beyond our horizon, and there almost certainly are, their stories are sealed off from us not by distance alone, but by principle. If there are civilizations in those galaxies, they will never receive our signals. We will never receive theirs. The question, are we alone, becomes more layered in that light. Are we alone in our observable patch? In the whole universe? The second question may be meaningful in mathematics. In practice, we can only ever answer the first. Does that make the idea gentler or more frightening? On one hand, it limits the scale of our potential loneliness. We do not have to imagine being the only life in an infinite expanse, only in a bubble defined by light and time. On the other hand, it sharpens the sense that there might be countless other islands of awareness, forever invisible, whose existence we can theorize but never confirm. The impossible thing here is not that the universe lacks an edge. It is that parts of it are unreachable in principle, not just in practice. There are regions whose light will never touch us, whose histories will run their course without ever intersecting our own. They are as real, in a physical sense, as the galaxies we see in Webb's deep fields. But they will remain, to us, abstractions. Learning to live with that is its own kind of cosmological maturity. To accept that our instruments, no matter how powerful, will always paint an incomplete picture. To know that some stories in the universe will never appear in any dataset we collect. And yet, to keep watching, to keep listening to the light that does reach us from near the edge of what is possible, knowing that beyond that line, the rest of the universe continues on, indifferent to our horizon. The questions that slip in through those cracks do not only live in light we can see, they also live in the weight of something we cannot. By now, the idea that most of the universe's matter is dark is almost familiar. Dark matter does not emit light, does not absorb or reflect it in any ordinary way. We do not see it directly in any Webb image or in any other telescope's view. We infer its presence through gravity, from the way galaxies rotate, from the way clusters hold together, from the way light itself bends as it passes by invisible mass. One of the clearest windows into this invisible skeleton is gravitational lensing. When a massive cluster of galaxies sits between us and more distant objects, its gravity warps space-time. Light traveling from those background galaxies follows curved paths. To us, those paths look like arcs, stretched shapes, sometimes multiple images of the same galaxy appearing around the foreground cluster. The universe, in those cases, behaves like a lens ground, not from glass, but from mass. Webb leans into this effect. Its deep fields are often chosen around massive clusters, precisely because the lensing magnifies and brightens galaxies that would otherwise sit below its detection threshold. In those images, you can trace long, thin smears of light winding around the centers of clusters. Each arc is a distant galaxy, distorted. The precise shapes and positions of those arcs tell astronomers how matter, both visible and dark, is distributed in the cluster doing the lensing. By fitting models to those distortions, researchers can reconstruct maps of dark matter. The light from ordinary galaxies in the cluster shows where luminous matter lives. The lensing pattern reveals where total mass lives. The difference between those maps is dark matter. Webb does not see it. Webb makes it impossible to ignore. These reconstructions do not stand alone. Astronomers combine Webb's infrared views with observations from X-ray telescopes, which see hot gas between galaxies, and with radio and submillimeter instruments that measure cold gas and dust together. These layers give texture to what we call the hidden framework. You might see a knot of hot gas in X-rays sitting slightly offset from the peak of the dark matter map, hinting at a past collision between clusters. You might see streams of cooler gas feeding into those knots, traced by other wavelengths. Step back from the clusters, and another pattern appears. On the largest scales we can map, matter in the universe is not arranged randomly. It forms a cosmic web, filamentary structures of dark matter, with gas and galaxies strung along them like beads. At the nodes where filaments cross, clusters and superclusters grow. Along the strands, smaller galaxies and groups form and fall inward. Gravity sculpts this web over billions of years, drawing material from voids into denser regions. Simulations predicted this web long before we could glimpse it directly. Now, with instruments like Webb, we start to see its threads more clearly, faint filaments of galaxies at similar redshifts, extending over vast distances. Cold gas channels feeding young galaxies, glimpsed in emission or absorption lines. These structures are not just background, they are the supply lines. The Webb delivers fuel to galaxies, allowing stars to keep forming, black holes to keep feeding. In Webb's deepest looks at the early universe, some of the dense structures revealed by lensing and by clustering seem to show that dark matter clumped into massive halos faster than the simplest versions of the standard model might suggest. Protoclusters of galaxies appear at redshifts where, on paper, such crowded regions should be rare. Once again, there is a timing problem. If dark matter halos grew too slowly, how do you end up with these knots of structure so soon? The answers are still being worked out. It may be that our estimates of how quickly halos merge, or how initial fluctuations in density behaved on certain scales, need fine-tuning. It may be that selection bias favors the most dramatic examples in our first Webb fields. Or it may hint at something more radical, nudging at the debate that has simmered for decades. Do we need dark matter at all? Or should we instead modify our theory of gravity? Some alternatives, often gathered under the broad label of modified Newtonian dynamics and its descendants, try to explain galaxy rotation curves and other phenomena without invoking unseen mass. They adjust the laws of gravity at very low accelerations, or introduce new fields that alter how matter interacts. These ideas have had successes in certain regimes, especially on the scale of individual galaxies, but have difficulty matching the full suite of cosmological observations that dark matter accounts for more smoothly. Webb does not settle this larger controversy. What it does is strengthen constraints at high redshift. The shapes and alignments of lensed arcs in the early universe, the way galaxies cluster along filaments, the distribution of mass in young protoclusters, all of these depend on how gravity behaves and on how much dark matter is present. As those measurements accumulate, they act like tests that any alternative to dark matter must pass. So far, the simplest reading is that some form of unseen mass remains the easiest way to explain the patterns. There is something almost painterly about the way this all comes together. When you look at a visualization of the cosmic web from a simulation, with bright lines of matter swirling and looping, it can resemble the background of a painting like Van Gogh's Starry Night. Not isolated dots on a blank canvas, but swirling strands, eddies, and flows. The difference is that, here, the brush strokes are data. Each point, each filament, has a weight and a velocity attached. Webb's role in that artwork is subtle. It colors in the galaxies that sit on those strokes. It shows you the tiny arcs that mark where the web's knots bend light. It reveals the star-forming regions at the intersections, the dusty cores where black holes eat and stars explode. In the images, you see only luminous paint. In the reconstructions, you see the invisible lines that hold it in place. Every time you look at one of those deep fields, it is worth remembering what is not there. The dark matter halos that dominate the mass do not glow. The filaments that link clusters together do not appear directly. You see their shadows in distortions, in the way galaxies cluster, in the timing of structure growth. It is like trying to understand the shape of a skeleton by watching how muscles and skin move over it. The impossible feeling here comes from inversion. The most important part of the picture, the scaffold that holds everything together and guides the flow of gas and light, never appears directly on the image. The arcs and stretched galaxies that Webb records are reminders, quiet and insistent, that most of reality is not what shines. And then there is us, made of the tiny part that shines, trying to make sense of the weight of everything we cannot see. Little animals on a small rock, staring at a sky that keeps refusing to fit our first guesses. After so many signals that bend or stretch the models, it is natural to feel a kind of vertigo. The scale is too large, the diagrams too dense, the language filled with phrases like tension and crisis. You may feel, somewhere between your chest and your throat, that sense of being slightly off balance, as if the floor you thought was firm has begun to tilt a few degrees. There is also a quiet cultural backdrop to all of this. Since Hubble's launch in the year 1990, and the rise of the internet soon after, images of the cosmos have become wallpaper for everyday life. Nebulas on phone screens, galaxies on laptop covers, deep fields printed on blankets and mugs. The universe arrives as decoration long before it arrives as problem. Most people see the pictures, not the arguments underneath them. They see the color, the spirals, the glowing gas. They do not see the years of work that go into calibrating a detector or the stubborn graph where two lines refuse to meet. In a way, the beauty filters the crisis. It is entirely possible to grow up in this era and believe that cosmology is a finished story, that the big things are known and only small details remain. Inside conference halls, the mood is different. Imagine a meeting room in the early 2020s. Rows of chairs, a screen at the front, figures projected in muted colors. A researcher stands there, pointer in hand, showing a plot where new Webb data do not sit where the old models told them they should. The galaxies are too bright, the black holes too massive, the expansion rate too high or too low, depending on which side you came in from. During the coffee breaks, the conversations circle back to the same themes. Someone leans against a wall and says, half joking, that it feels like living in a house where the floor has started to crack but the walls are still standing. You can hear tiny sounds, subtle shifts. No one knows whether to call in a crew to rebuild the foundations or just patch the visible lines and wait. people walk back into the next session with that feeling in their bodies. Not full panic, not yet. More like the unease of realizing that your sense of completion was premature. The models that guided your career, the diagrams you have drawn hundreds of times for students, are suddenly provisional again. From where you sit, listening, far from those rooms, you might feel something else entirely. When you hear the sentence, "We may be wrong about what we were most sure of," what rises first? Is it unease, the instinctive discomfort that comes when authority admits uncertainty? Is it a quiet thrill, a sense that the universe has not exhausted its surprises? Or is it, strangely, a kind of relief that even experts do not have everything pinned down, that our maps are still drafts? Films have given us one way to inhabit this disorientation. In Interstellar, the character Cooper begins as an ordinary person, a pilot turned farmer, pulled into a journey that throws him past black holes and time loops. He does not become a physicist overnight. He remains, mostly, someone trying to navigate a situation whose rules keep breaking his previous understanding. The story is urgent and loud, but beneath it lies a simple emotional thread. What do you do when the universe stops cooperating with your intuition? For many listeners, especially those outside the field, the experience of hearing about dark energy, or the Hubble tension, or galaxies forming too early, is not so different. You are not being asked to solve the equations. You are being told that the framework handed down as settled is shifting. The familiar comfort of "this is how it is" loses some of its certainty. There is a temptation, when faced with that, to slide into one of two extremes. Either to cling harder to the old story, treating any sign of revision as a threat, or to give up on the idea of understanding altogether, throwing your hands up and saying that if the experts cannot agree, nothing means anything. Webb's quiet gift is to offer a third option. It reminds us that most of what it breaks is not reality itself, but our description of reality. The universe has been doing what it does for billions of years without consulting our models. Galaxies did not assemble faster because we wrote equations that said they should not. Black holes did not grow with one eye on our textbooks. The cosmos is not misbehaving. We are recalibrating our story. Seen that way, the unsettling parts begin to soften. Instead of thinking everything is wrong, you might try, "We are being invited to draw again." The maps were never the territory. They were sketches that worked well enough, for a while, in the regions we had explored. Now that the exploration has gone deeper, the outlines need altering. There is a kind of comfort in that, if you let it in. Living in a universe that does not always fit your first ideas can make you gentler, not only toward physics, but toward people. If cosmology, one of the most precise, data-rich sciences we have, must still say we do not fully know, then perhaps it is acceptable for you to say the same in other parts of your life. To resist the urge to snap to judgment. To hold conclusions with a looser grip. You might notice the parallel in something closer than galaxies. Think of a person you believed you understood completely. A friend, a parent, a partner. You had a story about them in your head, built from years of interaction. Then one day you learn a detail, or see a reaction, that does not fit. They remember an event differently. They reveal a fear you never suspected. For a moment, it stings. Your story is incomplete. You misread some part of the map. If you resist that discomfort, you might try to force the new detail into the old frame, ignoring the mismatch. If you lean into it, the relationship can deepen. You begin to see that this person is larger than your first account of them. More complex, more layered, less predictable. Cosmology is in a similar position with the universe itself. Webb's data are those new details. They do not say that the old story was foolish. They say that it was, inevitably, simplified. As with a person, the choice is not between certainty and chaos. It is between a rigid story that cracks under pressure and a flexible one that can bend and widen. This is perhaps the deepest impossible thing that Webb confronts us with. Not a single galaxy whose mass seems too high, or a black hole whose growth seems too quick. Those may resolve into more ordinary puzzles as data improve. The harder task is accepting that our story about reality is unfinished and may always be unfinished, while still feeling some sense of peace. To lie here, listening, and allow yourself to rest inside a universe that is not fully mapped. To know that brilliant people argue in faraway rooms about expansion rates and dark components, and that those arguments will continue long after this night. To accept that the picture above your bed, the galaxy poster on your wall, is both true and incomplete. If you want, you can let that knowledge drop out of your head for a moment and back into your body. Notice the weight of yourself against whatever you are lying on. The rise and fall of your breath, the small sounds in the room, appliances, street noise, your own heartbeat if you listen closely enough. Out there, beyond the walls, telescopes circle and float and stare. Data streams in. Simulations run on distant servers. Papers are written and revised. Voices rise and fall in debates about the fate of the universe. In here, air enters and leaves your lungs in a quiet rhythm older than any model. You are, somehow, part of both. A living piece of the visible matter, trying to understand the invisible skeleton. A mind built to navigate rooms and streets, now reaching for numbers and distances it cannot fully picture. It is all right if that feels like too much sometimes. You can let the questions stay questions. You can allow the cracks in the story to be there without needing to fill them tonight. The universe will continue, indifferent to our confusion, generous in its light. The room will hold you. The floor beneath you, however metaphorically cracked in other contexts, is solid enough for now. The questions do not end when the room grows quiet. They settle, instead, into a different kind of silence. By now you have traveled a long way without moving. From the launch of Hubble in year 1990, through the first deep stare into nothing in year 1995, to the unsettling discovery of cosmic acceleration in year 1998, past the Nobel ceremony in year 2011 that seemed to fix that picture in place. Then onward to the launch of Webb in late year 2021, its first images in year 2022, and into the arguments and tensions of tonight. If you let all of that blur together, it does not feel like a list of milestones. It feels more like walking through rooms in a house that keeps secretly adding new doors. Just when you think you have seen every wall, a panel shifts, a corridor opens, and the floor plan expands. In that expanding house, Webb did not tear down the entire structure. It left some load-bearing beams, exactly where they were. The universe still began hot and dense. It still expanded and cooled. The cosmic microwave background still glows around us as the stretched afterglow of that first light. General relativity still predicts how gravity bends space and time, and its predictions still match what we see in lensing arcs and orbits. What Webb disrupted was not the existence of the Big Bang, or the validity of relativity. It disturbed something more emotional and less formal. The sense, widespread in the years before it launched, that cosmology was almost finished, that the major pieces were in place, and only fine details remained to be brushed in. The so-called impossible results that followed are better understood as questions with sharper teeth. Why is there so much structure so early? Why do some galaxies and black holes look more mature than the allotted time should allow? Why do different methods of measuring the current expansion rate refuse to agree? Why does the young universe, seen through Webb's eyes, seem more crowded, more chemically evolved, more hurried than our neat timelines predicted? None of those questions requires you to declare that everything is wrong. Many of the most dramatic early claims have already softened as data improved. Galaxies once hailed as surely at redshift beyond 13 turned out, under closer spectroscopic scrutiny, to sit nearer in time. Mass estimates have shrunk as models of star formation and dust have become more tailored to early conditions. Some of the most extreme universe-breaking headlines now read, in hindsight, like snapshots of a normal scientific process caught mid-sentence. That is important. In a culture that loves clean twists, it is tempting to frame every revision as a scandal or a revolution. But much of what happens around Webb is quieter. A claim is made. Assumptions are examined. New observations arrive. Numbers shift. Conclusions adjust. The structure bends but does not collapse. Not every shock is a foundational overturn. Sometimes the impossible dissolves into the merely surprising. And yet, even after those adjustments, something non-trivial remains. The early universe retains a faint air of overachievement. There are still more bright high redshift galaxies than many baselines expected. Supermassive black holes still sit at times uncomfortably close to the beginning. The Hubble tension still refuses to melt away into a simple calibration error. Dark matter still shapes a web whose densest knots may have formed faster than we are entirely comfortable with. In that sense, Webb has broken not the universe, but our sense of tidy closure. It has reopened questions that were drifting toward the back of textbooks. It has reminded us that, in a field that moves slowly, there can still be decades when the ground shifts under everyone's feet. And Webb itself is not the end of that shifting. On the horizon are new instruments and surveys that will look at the sky in other ways. Space telescopes like the Nancy Grace Roman mission will map enormous areas with exquisite precision, tracing the subtle distortions of billions of galaxies to weigh dark matter and probe dark energy. Ground-based observatories like the Vera Rubin Observatory will watch the sky change night after night, catching transient events and mapping structure over time. Extremely large telescopes on Earth will dissect the light of faint galaxies and stars with resolutions Webb cannot reach. Each of these, in their own domains, will likely play the same double role that Hubble and Webb have played. They will confirm some parts of the current picture with breathtaking clarity. They will also reveal anomalies we cannot yet name, places where our assumptions fray. If you step back further still, you can see a pattern running from those first Hubble deep fields through Webb's infrared portraits. A chain of ever deeper looks. Each time we stare longer and more sensitively into a small patch of sky, the canvas we thought was fixed has to be erased and redrawn in some corner. First we learned that an apparently empty spot is full of galaxies, then that those galaxies are more numerous and more distant than we imagined. Now that some of them have grown up faster and become richer in heavy elements than our first stories allowed. The images that mark those steps share a surface similarity. Scattered points, arcs, colored smudges. What changes underneath them is the story we tell. How quickly matter organizes. How gravity and expansion share the stage. How light remembers its journey. Through all of this, one thing has not changed. Short-lived beings, made of ordinary matter, continue to choose to understand. People whose lives span maybe 8 or 9 decades spend years refining a measurement that will adjust a cosmic parameter by a few percent. They accept, again and again, data that contradict their expectations, even when those expectations are tied to their own past work. The fact that you are still listening, this late in the story, is part of the same impulse. You could fall asleep to music, to fiction, to silence. Instead, you chose to let your last thoughts wander through galaxies, black holes, dark energy, horizons, and tensions. There is no practical advantage in knowing that the observable universe may hold trillions of galaxies, or that the Hubble constant refuses to be pinned down to one uncontested value. And yet, some part of you wants the picture to be wider, even if that width comes at the cost of certainty. Maybe that is what Webb has most clearly preserved. Not a particular model, not a specific set of numbers, but the relationship between a curious species and a reality that does not bend to its first drafts. The telescope's discoveries are unsettling, but they land inside a deeper continuity. We ask. The universe answers, not with validation, but with more complicated truths. We revise. We ask again. If a golden, icy machine with no emotions can become a reason for us to grow more humble, then the old boundary between observer and observed starts to blur. We built Webb. We pointed it outward, but its most lasting effects may be inward, reshaping how we think about knowledge, certainty, and our place in a story that is larger than any one generation. You can picture it now, if you like, before sleep pulls you the rest of the way under. Webb drifting at its distant halo orbit around the Sun. Earth balance point. Mirrors cooled. Sunshield taut. Instruments quietly counting photons that began their journeys when the first stars were new. Below, Earth turns, carrying continents of sleeping people and late-night listeners and overworked scientists staring at screens. Around all of that, trillions of galaxies continue to shine, some racing through their own early growth spurts, some settling into long, slow evolutions, some already torn apart by mergers we will never witness. Light leaves them in all directions. A thin fraction finds its way to one hexagon of gold a long way from home. In a small room somewhere on that turning planet, someone closes their eyes with the faint, strange comfort that the universe may never be fully understood. But it will not, for lack of effort, ever become boring. If that feeling stays with you, even a little, you can carry it into tomorrow. Ask one more question than you normally would. Look up for a moment, longer than habit requires. Share this story with someone who might need a reminder that it is all right not to have everything figured out. And when you are ready, you can let the cosmos fade to the background again. Let your attention return to the weight of your own body, the softness beneath you, the rhythm of your breathing. The universe will keep unfolding its quiet impossibilities. You, for now, are allowed to rest.